Welcome to our first video on Chapter 1, and welcome in general to Earth Science. I will be doing videos for each of our sections. Sometimes these videos will cover more than one chapter, but I will always be doing something for you for each of the lectures so that you can watch this and follow along on the PowerPoints at the same time. So I will be sharing my screen so that you can see what I'm seeing. I'm not just going to read the PowerPoint to you. There's no point to that because you can do it yourself. So I will sort of expand on some things along the way. And let's get started here. If I can share my screen, I will share this screen with you. And we will go to view the slideshow. So had you purchased a textbook, this would be the one that you would use. And this is the one that is keyed towards our lab manual as well. So this is on Chapter 1. For week 1, we'll do this, and then we'll do an astronomy section. So stay tuned for a second video coming up shortly after this. But we are going to be looking at things that make up Earth science, things that make up science in general. That's 1.2 here. We'll look a little bit at the solar system. We'll look a little bit at our Earth's own construction, 4 major spheres that are there. And you didn't know there were 4, did you? There. See, you're learning already. And then we'll talk a little bit about continents and ocean basins and things like that. But when we are talking about Earth science, it's a conglomerate of sciences. We include geology, which is sort of rocks and minerals and other kinds of things that have to do with our physical plant here. Oceanography, so we'll be talking about the oceans, but not just the oceans. We'll talk about seas and lakes and water and other kinds of things too. Meteorology, which talks about the weather. So we'll be talking about hurricanes and tornadoes and clouds and other kinds of things, and the atmosphere in general. And then astronomy, which is sort of my greatest love, if you couldn't tell already, which is the study of the universe as a whole, as well as its constituent parts, of which the Earth, pictured here behind me, is one part. Notice that that is astronomy and not astrology. We'll talk a little bit about what the difference is there coming up. So when we're dealing with geology in particular, we might think of a place like this in terms of the Grand Canyon, Arizona's magnificent structure there, which is carved out by the Colorado River. It's a mile deep, but to get down there, you often have to take the long and windy road that you can sort of see in our piece here. Now, on your own, I'm not going to do this in this video, but if you pull up the PowerPoint, you can click on some of these pieces that are here, and they will take you to outside videos that will expand a little bit on each of the concepts. So you can do that on your own. And this one will obviously talk about the Grand Canyon and a little bit more about geological processes. We'll talk more about that along the way in later bits and pieces. Earth science is an environmental science. We're talking about the environment in which we live and in which plants and animals grow and survive or not survive. We have natural hazards. We have hazards that are like hurricanes that are hitting right now as I'm making this video. Natural hazards also include impacts from outer space. That's natural. Tornadoes are natural. Nuclear meltdown at a power plant is not natural. That would be a people influence the Earth process, which is down here below. And one of the things we also deal with in environmental science are resources. What do we have in terms of what we can use? Where is it best to grow plants? Where is it best to not put a farm? Where is it best to dig for gold or dig for coal? Where is it bad to do those kinds of things? What about fresh water versus seawater? The world is mostly water, but most of the water is not really drinkable. So knowing our resources is important in terms of our planet, and this would all fall under the rubric of environmental science. Now, when we're talking about geological time, we're talking about a very, very long period of time. Our Earth is a little over 4.5 billion years old. We're sort of edging up till 4.6 billion years old because every year we get a little bit older. But if we were to form all of that, push all of that into one calendar, so we'd say the world was created on January 1st, most of what we take for granted as being part of the world actually didn't come around until the very end of December. In fact, dinosaurs weren't even around till the middle of December, and they were gone by Christmas and the day after. Human beings didn't come along until the last day, and you can sort of see all of these different things that are here. Now, you can go again to this link down below, and it will talk a little bit more about the very, very long periods of time. But for most of the Earth's history, most of us were not around. And when I say most of us, I mean plants, animals, and pretty much every living thing. For most of the history of our planet, we did not have animals. Animals came around really in mid-November in any good number. And in terms of moving onto land out of the oceans, it was late November. So we're really a late forming planet in that sense. When we talk about recent in terms of geology, we're not just talking about the things that were on television a week ago or a month ago or even a year ago. We're talking about things that go back hundreds of millions of years as being recent, because when you're 4.6 billion years old, 100 million years doesn't really add up to all that much. So we divide things into geological timescales, and we'll be talking about that when we talk more about geology. So Jurassic Park, for example, is probably the best example of that. The word Jurassic is one of those eras that we'll be seeing. And that, of course, was a long time ago. But even then, it was relatively recent compared to 2 billion, 3 billion years ago, because the Jurassic period was 100 million years ago or less. We have some wiggle room for some of those time periods. When we're dealing with science, one of the things we're looking for is patterns in nature. Why does the same thing happen over and over again? Why do we form things that we form in terms of molecules? Atoms form into molecules, molecules form into compounds, compounds form into plants and animals and substances that are around. Using that kind of knowledge to figure out what's going on out there is important. So what we're looking for when we're looking in science are things that are consistent. Water is H2O everywhere. H2 means there are two hydrogen atoms. O means oxygen. If you've got two hydrogens and an oxygen together in that right way, it's always water. Even if you've got impurities in the water, it's always water. Now, if it's H2O2, that's something different. That would not be the same. And that H2O2 doesn't necessarily become H2O. H2O, thankfully, doesn't typically become H2O2 because we would have a problem with hydrogen peroxide. That's not exactly drinkable for us. So when we're looking at science, we want to look at things that are consistent and predictable. If something out of the blue happens, miracles are actually not scientific. That's not to say things that are not scientific are not true. It simply means they're not scientifically true. And that's one of the problems we get into in the modern world with when we're trying to sort of figure out what's scientific and what's true. Genesis may well be true. It may not be true. But that's a matter of faith and religion. It's not a matter of science. No one writing the book of Genesis and the beginning of the world was ever thinking in these kinds of terms of what scientific inquiry is. They weren't thinking about history in the way we talk about history today. So we're applying different standards to that book if we're trying to make it scientifically true or we're trying to make it historically true, which are unfair to science, unfair to history, and unfair to the book of Genesis, because none of them were meant to do that along the way. So the scientific truth is not the only kind of truth that's out there. But when we're dealing with things that we want to understand how the world works and operates in a consistent and predictable way, this is what we do. We come up with an idea. We have a hypothesis. Whenever I put water at this particular temperature, it freezes. Whenever I put it at this particular temperature, it boils away. That can be a hypothesis. I can sort of figure out what happens to the water. That's untested. A theory is when I test it, and that happens again and again and again and again. So every time I boil the water, every time I put heat to it, 212 degrees Fahrenheit, 100 degrees Celsius, it tends to boil away. If I lower the temperature to 0 Celsius or to 32 Fahrenheit, then it freezes. That happens over and over and over again. Now, one of the things I might do from my observation is I might find in some places it takes more heat to boil. I might find that it takes less heat to boil. Then I have to figure out, why is that happening? It's usually not that much more or less here on planet Earth. But if you go up to Denver, where the air pressure is less because it's a mile high stadium in Denver, you're going to have different temperatures there. If you go to the Dead Sea, which is several 100 feet below sea level, then you're also going to have a slightly different temperature, only by a couple of degrees here and there. But then we can sort of figure out how that works as well. And that gives us a paradigm where we're looking at how water freezes or boils in different environments on the planet. And we can use all of that to gather more facts and figure out more things about what's happening. So this is sort of the steps that we would use. Raise a question: why does it always boil? Why does it always freeze at this? We collect information about it. We sort of test it in different ways. We construct our answers as to why that might be the case, and we sort of run it through tests. Sometimes it works and sometimes it doesn't. If it doesn't work, then we try again. Either we collect more data or we construct a new question. And eventually, when we get to a point where we are reasonably confident this happens a lot, we share that with the scientific community. But also, when we find out something doesn't work, we also share that so that other people can follow up on the investigations. Now, our universe, as far as we are able to determine now with our current technology and our current ideas, is a little under 14 billion years old. That number does change over time. It doesn't change radically and magnificently. It doesn't go from like 10,000 years to 1,000,000 years to 1,000,000,000,000 years and back and forth. But when I was taking this class 40 years ago, the number that we would have had there would have been about 20 billion years. So we've revised it up a little bit in terms of figuring out how the universe is going. The solar system, which is where we are in the universe, the sun, Sol, S-O-L, see, it's right there in the word, and the other planets are a little under 5 billion years old. So the universe has been around for almost 3 times as long as our solar system. Now, one of the ways in which we think that this formed was, as we look out into space, we see a lot of places that are filled with gas and dust, and they are sort of falling in on themselves under the weight of their own gravity. They're mostly hydrogen and helium gases, and they clump together. Eventually, it may come under enough pressure that it can spark a nuclear reaction in the center, and that becomes a star. You may have other clumps around that then will begin to form into planets. In fact, our largest planets in our solar system are Jupiter, Saturn, Uranus, not Uranus, Uranus, and Neptune. They're also mostly hydrogen and helium, just like the sun is. The inner planets are close to the sun. Because of that, the heat from the sun boiled away most of the hydrogen and helium. So what was left with is the stuff that doesn't boil away quite so easily. So they're metallic and rocky. So Mercury, Venus, Earth, Mars were sort of rocky clumps. Outside that, when you get far enough away from the sun that it doesn't melt things, we have a lot of ice. So particularly Uranus and Neptune are called ice giants. So we've started out as a gas cloud that fell in on itself. We had enough pressure and temperature increase in the center to spark a nuclear reaction that then formed into our solar system. And we'll talk a little bit more about this in the next lecture, so I don't want to go into too much detail here. But again, here's a link down below that you can go to see a little bit more about the nebular theory. The word nebula is Latin for cloud, so this is a cloud. Now, how would we know this? One of the ways we might know this is when we look out into space with telescopes, we're seeing different images of clouds like the nebula. We're seeing protostars where it's about to kick on the engine. We're seeing newly formed solar systems, and we're seeing solar systems like ours. Sort of like looking at a forest. You don't have time to sit there and watch the entire thing grow, but you can find seeds and saplings and young trees and mature trees and dead trees, and you can put the life cycle together. Even though you don't have time to watch the whole thing, you won't live long enough. We do that out in space as well with the solar system. So our solar system is a small part of the universe. The universe is much larger than the solar system. Our galaxy is much larger than the solar system. Our galaxy is 200 billion stars. We're just one star of that along the way. The sun is huge compared to our solar system. All the planets together don't come up to even like 1/100th of the sun. If this were the sun here, we can just see a sliver on the side. Here on the right-hand side, this would be the size of the Earth. You can stretch more than 100 Earths all the way across the sun. It is that large. Jupiter up here, or down here, sorry, is 300 times the size of the Earth in terms of how much mass it has. But if you hollowed it out like a gumball machine, you could drop more than 1,300 Earths into it. Saturn, as you can see, is almost as large. Though a cotton candy planet, it's a lot lighter and fluffier, so it is only 95 times the size of the Earth. Uranus and Neptune over here are 15 and 17 times the size of the Earth. All the other rocky planets are close to Earth size relative to these other things here. Earth and Venus are, in fact, almost the same size. Mercury and Mars are like half and third the size of the Earth. Our Earth has different spheres that are all interacting with them. We have the hydrosphere, which of course is, you think about the oceans. Hydro means water. It covers most of the Earth's surface in terms of percentage. So by far the overwhelming majority, 71%. That means only 29% is land. We have water in freshwater streams, lakes, and glaciers, and other kinds of things like that. But notice the freshwater is only 3% of Earth's water. The ocean is 97%, and the ocean is pretty much undrinkable because of its salinity, its salt content that's there. So when we're looking at it in this regard, this big cube here was all the water, the hydrosphere. We've got ground lakes and underwater kinds of salt lakes here, only about 1%. Freshwater is a little under 3%, which includes glaciers and our ice caps up at the poles. And then, of course, water in streams and lakes and other kinds of things like that. The atmosphere is very thin. If you've ever seen a globe and it's had a shiny surface to it, that shiny surface is probably about as thick as our atmosphere is. More than half the atmosphere only stretches 3 to 4 miles up. The tallest mountains, like Mount Everest, are 5 miles up. That's why most people who go up mountains like that have to take oxygen with them. And 1 out of 3 people who try to climb Mount Everest die of asphyxiation because they just can't breathe by the time they get up there. So as the atmosphere goes up and up and up, it gets less and less and less. And that's why it gets colder up there as well. Here we can sort of see in this graphic design where the air is thinning because it's colder. That's why you get mountain peaks with ice caps on them, even at the equator, even at the hot equator, because it's only hot down here at the surface. There aren't enough air particles to keep the heat going. And of course, we can go all the way up for dozens of miles and still have atmosphere, but it's less and less and less each time we go. And this band here, where we sort of say between 3 and 5 miles, we call that the top of the troposphere. We'll cover all of this in more detail as we're looking at things. But tropo, think of that, that's the same root word for tropics, and tropics are hot. This is where the heat is, and the heat comes in large part because of our blanket of atmosphere. If we didn't have the atmosphere, all the heat generated from our planet and absorbed from the sun would just radiate back out into space. Then we have the biosphere. That includes all life, so all fungi, all bacteria, all viruses, all human beings, all animals, all plants, all the different types of of life, and that goes all the way up into the atmosphere. We have sort of floaty particles of things that are alive up there, all the way down to the ocean floor, and then a little bit below that. We haven't explored too much further below that. Chances are good there might be a couple of extremophiles. Extremophiles, if you're like a bibliophile, you love books. If you're a radiophile, you love music, you love radio, you love records, things like that. If you're an extremophile, you like extreme environments. And there are some life forms that love it when it's really hot, love it when it's really cold. There are things that live in Antarctica, and there are things that live in volcanic zones. So chances are there are things that go several miles below the surface and several miles above the surface that we haven't discovered yet. But that's still a very thin layer when we're talking thousands of miles to the center of the Earth. No, Brendan Fraser is not the center of the Earth. But here we can see a couple of examples of that, including the extremophiles around these deep sea vents. This is a place where typically we don't have a lot of sunlight, if any at all, and yet there's a heat source here. So because there's a heat source generating energy, we have life forms around that. And it is actually pretty remarkable how that works. And then we have the geosphere. The geosphere is sort of all the solid ball of the Earth going all the way down. It's the largest of our four spheres because it's not just trapped on the surface the way the others are. And it consists of a crust. We live on the crust, and the atmosphere is just above the crust. The mantle, which goes down somewhat, and then the core all the way rested back way down. And it's divided depending upon how heavy the stuff is. The heavier stuff sink to the bottom first, the lighter stuff floats to the top. And again, we'll talk more about this as we're talking about geology. But you can see in this graphic, we have an inner core and an outer core. The inner core has solidified. It's not all that large when we're talking about, it would be smaller than the moon, it would be smaller than Mercury. It would be a large asteroid, but most of our core is liquid, which means it's sloshing around, which means that our planet, as it revolves around the sun and rotates on its axis, actually wobbles a little bit too because of this sloshiness that's there. Also, there are tugs from other things in our solar system that are pulling back and forth. But we have the highest density stuff in the center, and then we have lower density stuff as we go out beyond the core, but we have higher density rocks and lower density rocks as we get closer and closer to the top. And then we have what's called the lithosphere, which is solid and rigid where we live. But it's still floating on stuff that is solid but sloshing around a bit because we're on this liquid here. And that's why our continents drift and we get earthquakes and volcanoes and other kinds of things that happen. Our hydrologic cycle, we might call this just the water cycle. You probably learned this in school a long time ago. Water evaporates, forms into clouds. The clouds then rain or snow. It falls back onto land or the ocean. Sometimes it's done by plants. Sometimes it's done by I'm sorry, my phone is ringing and I'm trying to ignore it here. Sometimes it's flowing into the ground and becomes groundwater. Sometimes it will filter back out in the ocean directly. Sometimes it will coalesce into streams and rivers and often flow back into oceans too. But this is a cycle that continues. One of the parts you're probably not as familiar with the water cycle are volcanic activities that are involved in this. One of the reasons why Mars does not have a water cycle is because its volcanoes have shut off. That's not the only reason, but that's part of it. So what we have here is a complex system, and we'll talk about this in more detail when we're talking about both geology and meteorology. So our oceans go down maybe 3 miles. We can get a few spots that go deeper than that. Deep trenches can go deeper than that, but typically the ocean is about 3 miles deep. So that's not all that far if you sort of think about how far 3 miles is. Our continents will go up in general a little bit about 1/2 mile above sea level. But by the time you get into Rocky Mountains, like for example, Denver is a mile up, it's a mile high. The mountains, of course, themselves can go 3, 4, 5 miles up, but most of the area on our planet is not that high. So we're really living in a thin layer at the top of the lithosphere, the top of the crust. And here's what the Earth looks like. We have continents, North and South America, Australia, Asia, Europe. Asia and Europe we often call Eurasia because it's really one big landmass, and Africa. We sometimes call India a subcontinent because it used to be attached down here to Antarctica and it drifted up in part of the continental movements. The Pacific Ocean is a big plate under the ocean which is turning. We have regions on the side here of North and South America that are bumping up against it. Where it bumps up against, that's where it pushes up mountains. You can sort of see lots of mountains here. Over here, India's bumping up against Asia. We've got lots of mountains in that area. So it explains that. Here in the middle of the Atlantic, notice all the way from the north to the south, we've got what's called the mid-Atlantic ridge. The plates are pulling apart. And they're pulling apart and it's sort of refilling in as that happens with magma from underneath. But the only place where it is above ground from the south polar area to the north polar area is this little place up here called Iceland. And I've talked about Iceland in class before. This is the place where you can go and you can put 1 foot in Asia, Europe, Eurasia, and 1 foot in North America. And they're separating out year by year by year. I went there 50 years ago, put my feet in 2 places. I can't actually stretch far enough to put my feet where I originally put them because the island has widened so much. No surprise, there are lots of volcanoes there. There are lots of earthquakes there a lot of the time because that's what happens in these fracture zones and in these tectonic zones. We'll talk about what those mean. As well. We've got continental margins around the ocean basins. We've got the shelf where it's close to being above water and the water sort of comes in and out, the tide rolls in and out. Then at a certain point it drops off. We call that the slope. And then we've got the continental rises where we've got accumulation of stuff. Then in the deep oceans we have some trenches where things are separating out. We've got some submerged volcanoes. We call those seamounts. If they reach the top of the ocean, they become islands. That's what the Hawaiian Islands are, actually. And then we have continental margins and ocean regions which will separate out and form these plains. You have these huge areas in the Atlantic and Pacific and Indian Oceans that are just flat areas covered with water. I've talked about the mid-Atlantic ridge as being the place where you've got a lot of activity and it goes above water in Iceland. So as we study that, we're sort of studying the types of rocks that make up all of this along the way. Then on continents, we have shield areas, we have stable platform areas, we have mountain belts, especially in the North and South America area, the Rocky Mountains, the Andes Mountains, and also over in the Himalayas and in Europe, we have the Alps where there's some pressure that's forming there. We also have the Appalachian Mountains here in the United States. Those are actually leftover from when North America and Africa were bumping up against each other. Believe it or not, the Atlantic Ocean once upon a time did not exist, and North America and Africa were actually pushing against each other. That's rather interesting along the way. But we'll talk about all of these things later in our semester. But you can sort of see in this map here, we have what we call our shield areas, large flat areas. We have our mountain areas. Notice all the way from Spain and Africa over here through the Himalayas all the way up through Siberia. And it almost looks like it connects because remember, this is a global thing. It connects over to Alaska and then keeps going down the coast of North and South America. So it's really interesting along the way. We have some old mountain belts all the way up at the top here, all the way at the top here, over here in Australia. And then as I mentioned before, the Appalachians. See, this part of Appalachia used to be part of Africa over here before the two continents separated out. Again, our link at the bottom here, if you pull up your PowerPoint, you can click on that and see a little bit more about that along the way. So that's it for chapter 1. I think that's pretty much all I need to cover. Let's see, I'm going to do a really quick look here and see. Oh, there's one thing I was going to mention, and that was astrology. So here's the thing. Astronomy with an N and an M, astronomy rather than astrology with an L and a G. Once upon a time, people looked up at the stars. There were two types of people who looked up at the stars. There were those who tried to figure out what the stars were doing in terms of moving around in space and what they actually were. Those were the astronomers. Then there were those who looked up at the stars and said, I wonder if they're making us do things down here on Earth. And they were trying to predict what effect the stars might have on us down here on Earth. Those are the astrologers. Astrology is a religion at best. Some people call it a pseudoscience because it's not based on any kind of consistently predictable pattern along the way. You may think it is, but the truth is it's more bias confirmation and wishful thinking. If you follow your astrological signs and charts and other kinds of things like that, you'll find it really doesn't fit science. So it's not a science. I'm not going to sit here and say that it's absolutely untrue. Most of the claims that are made by astrologers actually end up being untrue. The fact that they say, oh, well, this alignment of stars means this. Well, there is no scientific basis for that. So in science, it is not true. And if they try to claim it's scientific, that's the problem. It just as any religion trying to claim that it has a scientific basis. They're not using the scientific methodology. Now, once upon a time, if you were someone who looked up at the stars and figured out the patterns and things like that, there wasn't a clear dividing line between astrology and astronomy. And that didn't really happen until about the 15 or 1600s. So people confuse them a little bit along the way. But astrology is a religion and perhaps a little bit about psychology, whereas astronomy is a science where you're looking at what's there, predicting the patterns, and trying to figure out what things are made of and how they operate. So they are radically different things along the way. So when we're dealing with earth science, we're dealing with astronomy, but not astrology. We're dealing also, as we mentioned before, with geology and meteorology and atmospheric things of that nature. And we're also dealing with sometimes a little bit of biology, but astrology is not one of those along the way. Now, I check my horoscope every now and then just for fun, because if it ever says, today is the day to stay at home and binge on Netflix and eat mint chocolate chip ice cream, I'll probably be a believer. It's like, okay, that sounds good to me, I'll do that. But for the most part, here's one of the ways in which you can test this if you want to test it scientifically. There are lots and lots and lots of sites on the internet that give you horoscopes, that give you astrological predictions. You can go to the different ones and they'll give you different information. In fact, I have done this before because I was doing a scientific test on astrology for a school project. And I had one astrological prediction that said I should stay at home and I should not engage in any business dealings that day. And I had another one that said today is a good day for dealing in business. They were literally exactly apart. Here's the other thing about astrology. Most of the astrological charts that are out there have been developed over the course of almost 3,000 years, sometimes a little bit more than that. And as I mentioned before, the Earth wobbles. It's moved enough in 3,000 years that the constellations no longer correspond to the dates that you think they do. Those dates that they have on there, even if we hadn't adjusted the calendar several times in between, are 3,000 to 3,500 years old, which means they're 3,000 to 2,500 years out of date. According to astrology, I'm a Libra, but the fact is I'm not a Libra. I'm more than a month away from Libra. And so are you, whatever chart you are. So here's something, if you are interested in astrology, I invite you to do it. I might even put this up as an extra credit thing for an extra credit board. Go and look and find out what your real sign is. It's sort of fascinating. And when we talk about astronomy in my next lecture, I'll talk a little bit more about precisely what the wobble is. So stay tuned.